Let's define the dot product. The definition of the dot product is as follows. If we have a vector A, let's say A1I, A2J, and A3K, and we have a vector B, B1I, B2J, and B3K. So we can tell right away that these two are three-dimensional vectors. We know that three-dimensional vectors can also be represented through this method, A1, A2, and A3. And vector B can be represented as B1, B2, and B3. If you've never seen this method of representation before, I will explain it very quickly. So here we look at vector A. It has direction I, direction J, and direction K. It has three directions, therefore vector A exists in R3, meaning that the vector is three-dimensional. So here we see dimension 1, dimension 2, dimension 3. This is how this method of vector representation, which we often use in math courses, this is how this method keeps track of dimensions. If I gave you another vector such as 3i plus 4j, then you would represent this vector as such. So now that we have covered how this method of vector representation works, we can move on. For the dot product of A dot B, the result of the dot product is A1 times B1 plus A2 times B2 plus A3 times B3. This is a definition of the dot product for three-dimensional vectors. Similarly, if we had two-dimensional vectors C and D defined as such, then the dot product C dot D would be C1 times D1 plus C2 times D2. And this is the definition for two-dimensional vectors. Now, there is one more thing that we are going to learn about regarding the dot product. For vectors A dot B, the magnitude of A times the magnitude of B times cosine theta, where theta is the angle between vector A and vector B, then this equation holds true. One thing to notice when understanding the dot product is that our inputs are vectors. As you can see, A and B are vectors. However, our output is a scalar. This is a magnitude, the magnitude of A. This is a magnitude as well, the magnitude of B. And cosine theta is just another scalar output because we know that the cosine function looks like this, where this is 1. So the takeaway is the dot product, you have to input two vectors and the output you will get is a scalar quantity. So the output will be a number basically. So now let's move on to the cross product. The cross product. The definition of the cross product is as follows. So let's say we have two vectors. So we have v1 and v2. And let's say that this is the plane that they exist on, because this is going to turn out to be pretty important. And what would be, let's say, v1 cross v2? Vector. Let's say that this produces v3. Well, this vector will be orthogonal to v1 and v2. That's an A. So let's figure out what orthogonal means in this context. If the angle between these two vectors is 90, and we have our v3 going up like that, then the angle between here and here will be 90, as well as here and here will be 90. So this is v3 right here, and it is orthogonal to v1 and v2. I want to give another quick example here. I'm going to change up the direction a bit. So let's say we have vector A and vector B, and they exist on this plane. If I say vector C is defined as B cross A, then this is what vector C would look like, where the angle between C and B are 90, and between A and C are also 90. And then let's say we have vector D, which is defined as vector A cross vector B. Then vector D would look like this. And as you can see, vector D looks different than vector C. And this is because the order of crossing matters for cross product. The order matters for cross product. For dot product, it does not matter. Because for dot product, let's say we have P1 equals 3, 3, and then P2 equals 1, 2, then P1 dot P2 is going to be 3 dot 1 plus 3 dot 2, which is 3 plus 6, which is 9. And similarly, P2 dot P1 is 1 dot 3 plus 2 dot 3, which is 3 plus 6 again. So we have 9. So just wanted to show that really quick. This means for cross product, direction matters. To figure out which direction the output of a cross product is pointed towards, we need to use the right hand rule. And this is a lot easier to explain when you can observe someone's hand. So I suggest you either learn this in class or you Google YouTube videos that show the right hand rule with an actual hand. Since I only have a pen, I can't really show you my hand. So other videos would be more effective to learn this rule, but I will not be covering how to calculate the direction of a cross product because there are more effective sources out there that can help you do that. So moving on. So here we have I hat, or J hat, and the K hat. And similarly here we have I hat, J hat, and K hat. So what I'm going to write out here is the cross product of these two elements. So I cross I is equal to 0. I cross J is equal to K. I cross K is equal to negative J. So negative J, just to make it more clear, is I cross K. For J cross I, we have negative K. Notice how when we flip the order of crossing, the thing that changes is the sign. So I cross J was K, and J cross I is negative K. And for J cross J, we have 0 again. And notice another thing, I cross I was 0, J cross J was 0, so anything crossed by itself should be 0. So K cross K is also 0. And moving on, J cross K is I, and K cross I is J, and then K cross J is negative I. And that completes our table. I will replicate this table for the dot product. So now we have the dot operator right here. And for the dot product, I cross I is 1, and anything not crossed by itself is 0. So I cross J is 0, I cross K 0, 0, 0, 0, 0. But j cross j is 1, and k cross k is 1. If you are interested in how the math behind this works, you should do some dot products and some cross products yourself and actually expand the products. And you will see that the information in this table actually relates very well to the definitions that we have made up here. And as I'm actually looking at this, I realized that I forgot to give you the rigorous definition of the cross product, so I will do that now. So the definition of the cross product, the rigorous definition, is if we have vector A, A1, A2, A3, and vector B, defined as B1, B2, B3, if we want A cross B, the definition is the determinant I, J, K, A1, B1, sorry, A1, A2, A3, and B1, B2, let me make that more clear, B3. If you haven't taken Math 164 or 165, this may seem a little strange, but I'm just going to go through it quickly with an example. So the cross product definition says that V1 cross V2 is I, J, K, that's the determinant, 1, 2, 3, and 2, 7, 4. I won't go into the details on how to get the determinant, but this is basically what it would look like. It's not very hard, so you can just Google it. It's actually pretty easy. So I and the determinant of 2, 3, 7, 4 minus j and the determinant of 1, 3, 2, 4 plus k and the determinant of 1, 2, 2, 7, which would equal 2 times 4 minus 3 times 7i minus 1 times 4 minus 2 times 3 times j plus 1 times 7 minus 2 times 2 k, which would equal 8 minus 21i minus 4 minus 6j plus 7 minus 4k, which would also equal negative 16i plus 2j plus 3k. So that is the cross product and the dot product, and have a nice day.